Friday it is. It's the 22nd, and because we are also currently finishing up a test on Mod 13 electrostatics, today's lesson will just be additional information on the next mod of study and will not affect anything with your current test. And it will not have a written assignment in it except to send me your notes. So let's also, we'll just say send me your notes. So I'm going to look for completeness in those notes, so I'll give you the heads up on that before we start. You'll notice as we end Mod 13 electrostatics that Mod 14 would normally follow. And Mod 14 is called something or other. It is called electrical potential. So you'll notice because the year is very rapidly coming to an end, we are going to skip that mod, and I will sprinkle a little bit of information from that into this mod, which is Mod 15, and we won't get to Mod 16, which is magnetism. So I'll sprinkle a little bit of that in this mod, and so we'll finish our year of physics together with Mod 15. So start your last section of your physics notebook with the divider, and it's Mod 15. And it is called electric circuits. Alright, so I'm looking at the time. Say I started at 12:20. Here I just don't want to put too much on you with the 3-day weekend, and you have your junior thesis to polish up, so I'm going to try to keep it a little shorter than normal. So let's just start with our definitions, basic understanding of electricity running through a circuit. So what is a circuit? A circuit is a closed loop, emphasis closed, that carries electricity. So let's take a minute there and draw an example of a circuit. So we're going to have some sort of source here. We'll define that a little better in a minute. And a wire. And we'll say this is like a perfect wire through which electrons flow perfectly. And so again, this is a theoretical wire. And that is called a circuit. So it's a closed loop. Let me indicate to you what happens if I break the loop. So now this one is an open circuit, so you're going to have to draw two of them. So this one is a closed circuit. And this one is an open circuit. When you have a closed circuit, electricity will flow. This one has no flow. And this right here, if I draw it like that, I could easily take that little flappy thing and close the circuit and open it, close it, open it. Guess what that is? Here's one on my wall. I think you can tell what I'm doing. This is a switch. So when the switch closes the circuit, the electricity can flow, and when the switch opens the circuit, it stops flowing. It takes a closed loop for electricity to flow. So make sure that note is very clear. Let's talk about we'll go ahead and close the circuit here. Some source will get, again, better at indicating what this is in a minute. The wire through which the electricity flows, we have closed circuit, so we've got flow, going, source, and flow, so we're good. What happens if a wire here touches, say we're trying to operate something. I'll put a little light bulb here in our circuit, and we've got lots of time to expound on that. But just for now, we're going to let the light work because the electricity is flowing through it. But what happens if something like this occurs? What if a piece of this wire touches a piece of that wire? So that could actually happen inside of your lamp. Maybe you have some electricity flowing and somehow there's a fray and this touches that. It turns out that electricity will always follow the path of least resistance. Sort of like if you were stuck in heavy traffic, you're going to take the route that's the easiest. So guess what we call that? A short circuit. The problem with a short circuit, it causes heating. Because we have no resistance from the light and it's just going around and around and around quite quickly, and it's short-circuiting, causing heat and maybe even a fire. So that's why we have fuses inserted in our circuits, and we'll talk about those again later. But they will be indicators that the flow has increased too much and it'll break the circuit. It'll actually open up the circuit and stop all flow. So that's what a short circuit is. So I'm sure you've heard of these things before, and hopefully that makes sense to you. All right. So all this came from the word circuit. So we talked about a closed circuit, an open circuit, that led us to the word switch, and a short circuit. All right. So the next point, or set of points of interest is going to be talking about the actual flow of electricity. So let's see what that is. The flow of electricity that we talked about in this circuit. So let's say, again, here we have our source, our wire, and we have the flow of electricity. And let's take a little picture of, say, right there, where, well, it looks like I opened the circuit. I don't mean that. So say I'm going to emphasize that spot right there. So this is a part of the wire that I've pulled out just for us to look at. So I've magnified it so we can see molecularly what's going on. So we'll make it a little longer. All right, so here's the wire, and inside the wire there is an atom. For simplicity's sake, I'm just going to say that the nucleus is a positive charged nucleus, and the electron on the outer shell there is a negative charge. So it turns out that it's like a copper wire. This thing is full of copper atoms, and they don't look like that. I don't remember what the atomic number is for copper. I'm sure you do. But there's a lot more protons than one, and on the outer shell, I'm not sure how many negative electrons there are in copper. But for simplicity, we know that there's going to be a positive charge in the nucleus overall, and there's going to be one electron out on the outer recesses of this atom. So I'm going to draw it like that, and next to that is another positive with their negative outer electrons, and so on. So I'll just draw 3 of the many millions that are there. So what it turns out that when there is a push allowed, these electrons are not very held. So electrons in, what is this material when electrons flow easily through it? Electrons in a conductor, such as copper wire, are not held tightly. They are not bound with a whole lot of glue to their position, and just with a little bit of push, so we can give them a little bit of, shall we say, coercion to move. So with a little bit of push, these electrons will easily bump from this atom to this one, and at the same time this one to this one, and so on and so on. So that is what is actually happening when we see our flow of electrons. And these negative ones will flow toward the positive. So you might wonder, why is the arrow going that way on your drawing? Coming to that. But actually we know that the negative electrons are piling up and going in the positive direction. So in engineering, however, we are not going to look at these particles moving in this direction like they really do. So we're going to draw a line and we're going to step over it. We're going to cross the Rubicon. We're not going to look back because we want to be fit for the kingdom of God. Without looking back, we know that the negatives charges are the ones that are moving through the wire. We know they're going from the negative to the positive side of this source. However, can you realize this as an engineering student for a few seconds, if not a whole lifetime? I would like you to imagine, instead of the negative charges going that way in my diagram, how about if I imagine the negative charges are still, they aren't, but imagine it. Can you see that it may look like, from that perspective, that the positive charges are going that way? Have you ever been in a car wash and you know the car is still, at least for part of it, and the whole mechanism is moving past you, and you have that feeling, sort of unsettling, that you're moving forward when you're not. The brake is on and they had you set it, so you're in park, you're not moving, but you have that weird feeling that you are. So motion is sort of relative to who's looking at it. So can you possibly imagine this scenario as the electrons still and the positive charges going the other way? Can you do it? Well, why? Why live a lie? Well, mathematically, engineering, in the engineering world, it's just nice to have all the mathematical equations that bleed out of this to be positive. So if we're dealing with negative electrons all the time, we have negative signs all over the place, we're positive people. So what we do is we are going to always, when we cross the line, we're always going to draw our electric circuits as if the positive charges are moving in this direction instead of the negative charges going the other way. It's like, alright, so it's mathematically the same. Mathematically the same to allow the positive charges to move, let's just say, to allow the electron, the current, that's what we're trying to say, the electron current, to allow the current to move from positive to negative. And we're going to draw all our circuits that way, and it's just it's just mathematically simplifying. We like to simplify our lives mathematically, don't we? And there's another story behind this thought. And we actually are going to call that is called the conventional flow. When we know the real flow goes that way, but we're going to draw it as if the real flow goes the other way. And it's called conventional flow. Benjamin Franklin, he had the idea a long time ago that that there was a positive and negative side to a source. And he had the idea, they knew how to use and construct batteries sources a long time before they understood what was going on inside of them. So he conjectured, and it was purely conjecture, that the positive side had these excess of particles, which we now know are electrons, and that they were indeed flowing this way. We now know they are negative charges, and they are excess that is here, and it flows toward the positive. We know that. But many, many, many years have gone by, and many, many electrical circuits have been drawn by our electricians, starting with Ben Franklin, and we're not going to go back and change them all, because guess what? Mathematically, it all comes out the same. And because the speed that these electrons go doesn't really matter whether they're going this way or that way, it's almost instantaneous. So we're going to go with conventional flow. Sometimes that is called something else. I saw it. It is called whole current. That name comes from when the electron jumps off of the atom, it creates sort of, for a very instantaneous instant, a atom there with no electron. But concurrently the next electron is coming on, but in that little instance it creates a hole where there's no electron. So it's also referred to as whole current. And whole current in conventional flow, it always goes from positive to negative. And that's the way we're going to do it. So, all right. I will look at the time. All right, let me just end with one more discussion of, we'll define current, because I have the word right there. So I don't want you to be left hanging with that. The word current, we'll end with that today. So current is the flow of electrons in a circuit. It's like thinking of current in a stream. So like current in a stream is a good way to think about it. The electrons flow through their circuit like water flows through a stream. The current has a unit, and the unit for current is the ampere. And sometimes we call it amps. And sometimes we call it A. It is a measure of coulombs per second. So how about that? Coulombs is a measure of charge. How many of these charged particles are passing a point per second? And that is called the amperage. It turns out that when we're talking about current and amps and amperes or A, that there's a symbol. Now this is different than the unit. There's a symbol for current. When we use current in our drawings, it is indicated with the I. I don't know, on lowercase I don't know the history behind that. So just be aware when I say I on my diagrams, that I'm talking about current. All right. Oh, and one more thing, always one more thing. The current amperage is a metric unit, so you can have milliamps, you can have microamps, you can have nanoamps, you can have kiloamps, you can have megaamps. So just be aware that the dream unit, the dream is alive, in physics class, the dream unit is amps. So that's what we will convert anything that is in a metric form other than amps. We will convert it to amps in our formulas to come. All right, I've set the stage and we will pick it up there. Your assignment, which is today's Friday, so we're off Monday. By Tuesday at noon, please send me a picture of your lovely, lovely notes. All right, have a good weekend. Bye.